Today, we're taking a deep dive into the constellation Lyra. Now, it might look small, but it's really a treasure trove, a natural laboratory in the sky that holds clues to stellar evolution and even to the future of our own sun. We're going to break down its most brilliant stars, its ghostly nebulae, and the ancient myths it inspired. So, we'll be tackling 5 key areas. First, we'll get our bearings and pin down its location. Then, we'll investigate the incredible stars it contains. After that, we'll witness a star's final act, explore the Greek myths behind the constellation, and finally, look at Lyra's lasting legacy in science and culture. Let's begin. All right, first things first, let's get oriented. Before we can really appreciate what's inside Lyra, we need to know where to find it on that vast canvas of the night sky. Lyra covers just 286.5 square degrees of the sky, which actually ranks it 52nd out of the 88 modern constellations. But, this small size is deceptive. Its scientific density, as we're about to see, is astonishingly high, which makes it an absolutely prime target for study. What's great about Lyra is its global accessibility. As you can see, if you're anywhere between the North Pole and about 40 degrees south latitude, you can see the whole thing. It's especially prominent for those of us in the northern hemisphere, where it passes almost directly overhead during the summer. And finding Lyra is pretty straightforward for anyone familiar with the prominent asterism known as the Summer Triangle. Its brightest star, Vega, forms one of the vertices of this triangle, with the other 2 points marked by Deneb in Cygnus and Altair in Aquila. It's a really reliable celestial landmark. Okay, so now that we know where Lyra is, let's explore what's inside. This constellation is home to a remarkable collection of stars, some that set the very standards for astronomy, and others that are true gravitational monsters. We'll start with Alpha Lyra, better known as Vega. It's a spectral class A0V main sequence star, sitting about 25 light-years away from us. Its historical importance? Well, it just can't be overstated. For decades, astronomers use Vega as the fundamental calibration point for the magnitude system, defining its brightness as 0. This created the baseline against which all other celestial objects could be measured. Vega's role as a trailblazer goes way beyond photometry. In 1850, it became the very first star, other than our sun, to be photographed on a daguerreotype. And not long after that, it was the first star to have its light broken down into a spectrum, which really kicked off the era of stellar spectroscopy and let us probe the chemical makeup of distant suns. Now here's where Vega gets truly extreme: its rotation. At its equator, it's spinning at a staggering 274 kilometers per second. It completes a full rotation in just 12.5 hours. To put that in perspective, our sun takes 27 days. This incredible speed has some serious physical consequences. And this illustrates those consequences beautifully. The intense centrifugal force causes Vega to bulge out at its equator and flatten at its poles, distorting it into an oblate spheroid. This shape also leads to a phenomenon we call gravity darkening. The poles are closer to the star's center of gravity, so they're hotter and brighter, while the stretched-out equatorial region is cooler and dimmer. So Vega isn't a uniform sphere at all, but a complex, spinning object with a variable temperature. Next up is Chiliac, a system where we get to see gravity at its most ferocious. We're looking at a pair of stars orbiting incredibly close to one another. One of the stars has expanded so much that it has overfilled its own gravitational boundary, what we call its Roche lobe. Its material is now being siphoned off by its companion, forming a huge churning disk of superheated gas. It is, quite literally, a process of stellar cannibalism. Lyra has other crucial stellar objects too. The star RR Lyrae is the prototype for a class of pulsating variables. Their pulsation period is directly linked to their absolute luminosity, which allows us to use them as standard candles for precisely measuring distances to things like globular clusters. And then there's Epsilon Lyrae, the famous double-double. To the naked eye, it's one star, but binoculars split it into 2, and a telescope reveals that each of those 2 stars is itself a binary, resulting in a gravitationally bound 4-star system. Moving on, we're shifting from the lives of stars to their deaths. And here we find one of the most famous deep sky objects of all, the Ring Nebula. What we see here is a glimpse into the distant future of our very own sun. And that's exactly why this is so important. When we study the Ring Nebula, we're not just looking at some distant curiosity. We're peering into a cosmic crystal ball, seeing the final chapter for stars just like our own. M57 is what's known as a planetary nebula. Now, that name is a historical misnomer. It has nothing to do with planets. It's actually the expanding, glowing shell of ionized gas that was shed by a red giant star as it entered its final phase. This particular event happened roughly 6,000 years ago from our perspective here on Earth. At the heart of the nebula is the star's core, a white dwarf. It is incredibly dense and searingly hot, with a surface temperature of 120,000 Kelvin. It's the intense ultraviolet radiation from this stellar remnant that energizes the surrounding gas and causes it to glow, like some kind of celestial ghost. Having explored the science, let's turn to the humanities. The name Lyra isn't just a label. It comes from one of the most powerful myths of ancient Greece, a tale of music, love, and loss. According to the myth, the very first lyre was fashioned by the god Hermes from a tortoise-shell. He later gave it to Apollo, the god of music, who in turn gifted it to the mortal musician Orpheus. It was said that the music Orpheus played was so enchanting it could charm animals, trees, and even rocks. The central myth revolves around Orpheus's wife, Eurydice. When she died tragically, a grief-stricken Orpheus journeyed to the underworld to bring her back. His sorrowful music moved Hades, ruler of the dead, who agreed to let Eurydice return, but on one condition. Orpheus had to walk ahead and not look back at her until they were both fully in the world of the living. As he stepped into the light, consumed by doubt, he turned. And in that instant, he lost her for a second and final time. The myth ends with Orpheus's own death, after which the gods placed his lyre in the heavens as a constellation, a symbol of the power of art and love, but also a memorial to fatal human weakness. Finally, let's bring these threads of science and culture together to see how Lyra's legacy continues today. Lyra's influence extends far beyond Greek myth. The Inca people saw it as a multicolored llama deity. In more modern times, science fiction has often turned to its brightest star. In Carl Sagan's Contact, Vega is the source of the first confirmed interstellar message received by humanity. And in the film K-Pax, it's the supposed home system of the enigmatic protagonist, Prot. So in the end, Lyra is something like a celestial tuning fork. Through its pulsating stars, it helps us measure the universe. Through the Ring Nebula, it shows us the future of our own sun. And through its myth, it resonates with timeless human stories of love and loss. This constellation has served as a benchmark for brightness, a laboratory for stellar physics, and a canvas for our myths. It has consistently provided answers to some of our most fundamental questions. And so it leaves us to wonder, as our instruments and understanding evolve, what new universal constants will Lyra help us to next?